All right, sorry about the delay. So today we are going to continue our exploration into reinforcement learning. This will probably be the last kind of math heavy class for a while. After this, we will start talking about more like how do we select data for RL and how do we evaluate our models, and then we'll kind of build from there to things like using instruction following models as agents that interact with the external environment. But first, some logistic stuff. So I sent all of the groups that requested access to Tinker an API key to the member who submitted the form. Please let us know if you're having issues. Some groups are having issues with their key not working. I will try my best to get new keys if needed, but
Who should I contact? I think I contacted somebody already.
oh, did you send an email
I
to the
sent an email to you.
on the instructor's account?
Yes.
Okay, I need to check that. So, good job for contacting me. So your key doesn't work?
Yeah, I'm having issues with it. So you said other people are having issues with it.
Yeah. So okay, because they literally gave me no instructions on the key. Rather, they just like sent me, here are a list of API keys.
Yeah, and then as soon as I tried to use it, it said there was like a billing issue.
Okay, yeah, someone else saw the same error. So
it's not just in my computer.
yeah, no. Someone else has also seen that error. So I will try and figure that out with their hopefully human support this time, but we'll see. Can YouTube folks get keys? No, unfortunately not. We have a small number of keys for the class projects. All right, so there was something else I wanted to discuss, but I forget, so we will just continue with the class. Okay, so where we are now is we talked about the reinforce algorithm in the last class, and we talked about reward models in the previous class. So at the start of this class, I just wanted to address a question that some of you had last time, where I don't think I gave a proper answer. So again, this was the formula that we wrote down for what we want to maximize with reinforce, which is the expected reward, right? And here I'm writing it down for a particular prompt X. Now, we can expand this into a sum over all possible y's of the reward associated with that particular y times the probability of our of that y under our policy model. And then we want to differentiate this thing and take gradient updates to increase the probability of high reward outputs, decrease the probability of low reward outputs. So we wrote the gradient of this j function as rxy times the gradient d theta of this thing. And so some people had asked, well, we obviously cannot compute this for all possible y's, so we're going to sample one or some small number of y's to do this. But in the reinforce algorithm, we introduced this log trick, right, to make this a gradient a function of a log probability. And so one question is, why can't we just directly, so maybe I can write this down, why can't we just sample a few y and compute like the average of this quantity directly, right? Because we can we can differentiate through this probability p theta of y given x. So of course, it is just as convenient to do this as, well, maybe a little less convenient to do this than to use the log probabilities which we have when we're producing the y. But the real answer is no, because if you think about this sampling process and computing this average, if you look at the expectation of what you're doing, right? So if we compute this, where the y again is drawn from our policy model, and it is over the thing that we're averaging, which is this, you'll note that this expectation is not actually what we want to compute, right? If we write this out as a sum over our samples, we have an extra term here, which is the probability of y given x times the reward of x comma y times this. So to be clear, this is not what we actually want to estimate up here, right? We have this new term, which is coming from the fact that we are drawing these samples from our policy model, right? So when we're computing our expectation of what this quantity is going to be, we always have to multiply by the probability of that drawing that sample. And if you'll note that the log trick was simply to multiply by this quantity and also to divide by this quantity, right? So to correct for this, we would like to divide by this term. And dividing by this term just yields the same log trick that we discussed in the last class. So this is the real reason why we are switching to the log probabilities, is that dividing by this quantity within the sum yields the log trick. So hopefully that clears it up. If you just do the sampling with the raw probability, you are not going to get your unbiased estimate of the true gradient of the expected reward. You have a question? Yeah. Yes, exactly. So the reason why we want an estimate of the expected gradient, because we can never enumerate all possible y's. And so if you're just going to sample a couple y's, you need to use the log probability in order to get an estimate of the correct gradient. Yeah. Okay. So that is one question. The other thing that we left off with at the end of next class was this discussion of the KL divergence and how, subtracting this KL term from our reward can kind of keep the model from deviating too much from the SFT model that we're starting with. So in this class, we're going to get a little bit more complicated than that. So as you'll see throughout this class, we will keep introducing more and more things into our J equation, our J sub theta, to basically prevent the model from deviating too far in any one direction. So far, we've talked about this KL penalty as preventing the model from deviating too far away from the SFT model. In this class, we will also talk about preventing the model from deviating too far from the previous policy model. So like if I sample a couple y's from my current model and I get rewards for them and I want to increase the probability of high reward samples, one issue I might have is taking too big steps away from our old policy. And all of this is kind of related to reward hacking and degeneration of the model, where maximizing the probability of some response may degrade its performance on many different other tasks or prompts. And so there's a lot of machinery that's actually used under the hood to prevent the model from getting destabilized, and essentially everything boils down to taking very small steps in the direction of either increasing the probability of a high reward sample or decreasing the probability of a low reward sample. But you never want to take huge steps in any one direction, as people have shown that results in just lower performance overall. Yeah.
So what exactly is the issue with this again? Sorry, the thing.
In this particular case, so this was just for those who asked, can't we just sample a bunch of y's and compute the average of this quantity?
Yeah.
It basically is not giving you an estimate of the gradient that you actually want, which is up here. So you can see that it's close, but it's off by this term here. And so if you want to correct for this term, right, by dividing by this p theta y given x, like divide everything in this sum, then you get exactly what we saw in the last class, which is the reward times the log derivative of the log probability. Okay, yes?
So before, I think we got to the expectation from dividing and multiplying by the p theta. Here we're saying that we should get to the expectation because we're not able to sample y's. So
ideally, imagine if this reward itself was a differentiable function of theta, then we wouldn't have to do any of this. We could just compute the reward and differentiate directly through that through the y, right? So this y here is what is produced by our model. However, we already talked about the sampling process for y, making it non-differentiable. So all of these are essentially tricks to put some term in our j where we have some way to differentiate through our model parameters. So the probability of y given x or the log probability, those are all differentiable, right? Because we compute those using that full softmax distribution and we can backprop through everything. But the hard sample y here that we actually get when we compute when we pass this prompt through our model and then pass this through our reward model, this is not something we can differentiate through. There's no way for us to get a signal through theta or model parameters through this. Yeah. Okay, so let me just rewrite another thing that we talked about from the last class, which is the advantage A y, which we saw was this reward term minus a baseline quantity, right? Which this baseline could be a function of the prompt. And I wanted to just enumerate some of the baselines that we see today in reinforcement learning with LLMs. So we will not be covering the most kind of commonly used by the standard RLHF, but I still wanted to kind of write some of these out. So this is called a baseline again, and remember that it serves to kind of center the rewards that you're getting on your generated samples so that you only actually take an update and increase the probability of something when it's better than the model's usual output, or worse than the model's usual output. Okay, so here we talked about the mean batch stats in the last class, and we decided that this wasn't a great way of computing a baseline because all the prompts in the batch would be different, and so it's hard to compare the reward across different prompts. Maybe if you had a large enough batch, this might be effective, but your batch size also is limited by the compute that you have. The other thing we briefly talked about, and we'll talk more about today, is group stats. So here the stats all refer to like mean reward. So in a group stats, I can take one prompt and generate multiple y's for that, compute the reward for each y, average it, and use that as my baseline. So we'll come back to this. This is actually one of the dominant approaches today, but wasn't last year. So it's challenging to teach this part of the class every year. All right, and finally, what actually is used to be the dominant approach and now is still used today is what's called a trained value function, also called a critic. And so the idea here is that you train a separate model to, given the particular prompt, predict what the model's average reward is going to be on that prompt. The value function here is a little more complicated, well, a lot more complicated than that. Instead of just taking in the prompt, it actually takes in the prompt plus all the tokens the model has generated in the response up till some point. And then it tries to predict the reward, assuming the model completes that response at the end of the response. So basically, it's saying something like, okay, the prompt was write a story about unicorns, and so far you've generated, Bob was a cow. At this point, maybe your story is going to get a low reward because you have introduced a character who's not a unicorn. So the idea is that this value function can not only predict, what your expected reward will be given a particular prompt, but also given a partially generated response from your model. So some issues with this are it's essentially just the same setup as a reward model, where you initialize this value network with a giant SFT language model, and then you put a head on top of it, like a linear layer, scalar linear layer, just like in a reward model, except this time, given the prompt and the partial output, you're training it to predict the final reward that sample got. So let me just write out some properties of this. We're not going to talk too much about this in detail or the actual training algorithm for this, which is called general advantage estimation, just because it's complicated. It's not really clear if it's worth spending class time, but I will give you some pointers so that if you're interested, you can study this further. So basically, it takes the prompt X and partial response, and we'll use our notation here, meaning all of the tokens of Y before some position I, and it predicts the reward at the end of this full response. So obviously this isn't perfect, right? I could start my unicorn story with Bob is a cow, and it might still be a great story about unicorns, right? I don't have full information in order to predict the reward. However, I might be able to get a at least better than random idea of how the model is doing given some output, right? If my response, partial response is Bob is a cow, Bob is a cow, Bob is a cow, repeated like 50 times, it is probably pretty straightforward for this value function to say that this will be a low reward sample. Okay, so it's trained just like a reward model with a scalar linear layer on top of the final layer hidden state at I. But here we're not going to use the Bradley-Terry model. We're not trying to predict preference judgments. We're simply going to use our L2 loss or square loss to predict the reward. And then the final thing to note is that our reward model is frozen, right? So unlike the reward model, which is frozen during RL training, the value function is trained alongside our policy model p theta. And that's because the value function is constantly getting samples from the policy as input and partial samples and trying to predict the reward. As your policy model is changing, you may need to change your value function as well to get a better estimate of things that your model is actually generating at this point. So at this point, just some kind of high-level summary of what we have in our machinery. Let me just write this down, and I'll take your question. So at this point, if we are using a value function, we have our policy model, p theta. This is a language model that we are updating, and we want to make it its responses better. We have a reward model, which is often the same size as the policy model, or it could be from any other language model that has been trained and then fine-tuned using the Bradley-Terry objective that we saw. And we also have a value network, and this thing is also initialized from a big language model and trained to minimize the difference with the final reward of the sequence, starting from individual positions. So you can see that we want to train this policy model p sub theta, but in order to do so, we have to keep two other giant models in our GPU memory, right? We have to keep the reward model and our value function if we want to use one of these. So all of this were used in the original RLHF paper and the Instruct GPT paper from OpenAI. And so this setup became very common. Presumably, they tried many other things, and this was the setup that worked best. And so most LLMs today are trained using all of these, the separate reward model and the separate value function. But it is very compute intensive. So what we will see as we move towards GRPO, which is the kind of newer innovation, is that we have this idea that we want to make it as compute efficient as possible. Like if we can get rid of the reward model and get rid of our value function, then things become a lot simpler. We just have one model that we're updating. And so how can we get that done? That's kind of where we are moving towards. Yes?
Yeah. What is the L2 loss thing that you said?
Oh, it's the square loss that we saw in, so it's just if you have a O is your target and let's say, I don't know, Y is your, I've used Y a lot. Let's say T is.
Can you move the thing up? It's blocked by.
Oh, sorry. So let's say O is your target and P is your prediction. It's just this quantity or this. But you can use many different losses for this. Okay. So I'm not going to talk more about this value function in this semester. If you're interested, you can read interested in how it's actually trained. You can check out some online resources. I'll put them up on the website. But what I want to get back to now is our coverage of the KL divergence penalty, and just talk a little bit more about what kind of effect that might have on the model when we add this penalty.
Professor,
Yeah.
can you explain why is it like partial response YCI there? Like usually the reward is computed at the end of the sequence.
Right. The reward is computed at the end of the sequence. And remember, your baseline is trying to give you a sense of like how good is the model on average at this particular prompt, so that you have a better idea of if your current sample is better or worse than the usual behavior of the model, right? So if you have a trained value function, the idea is that it can give you a better estimate of the baseline performance of that model. Like you're actually training a model to tell you, given this prompt and given this part of the sequence that has been generated so far, what will be the final reward assigned to this sample? Like, if you were to unroll from that point infinite different generations from the model, what would be the average reward that you get at the end?
It's sort of an expectation, not an
Yes.
actual reward.
Yeah. However, of course, you can never train with that true, expected reward, and so we're approximating it by just a single sample or a small number of samples. Yeah, but the idea is that also here, your baseline is now different at every token of the response Y. Instead of, if you're using like the group statistics, then those are just computed at the very end of the sequence on top of the reward. But this might give you a better idea on, if I wrote like Bob is a cow and my expected reward tanked after that, maybe this was not a good decision that I just made when I generated the word cow. So, things like that are part of the intuition behind why we might want to train network. Of course, you might ask, why do we need a big language model used in our value function? And the idea is kind of the same as why do we have one for a reward function? You need something that has at least some level of language understanding capability in order to judge, like how good is this response going to be to this given prompt, right? It requires a lot of understanding of both the prompt and the partial response, and so that's why they generally initialize it with a language model and then fine-tune it. Yeah. Yeah. So it's a little more complicated than that. I don't want to get into it, but it's generally some sort of discounted version of that final reward that takes into account like how many tokens have you generated so far? Because if you've only generated a few tokens, you're likely going to have a much worse estimate than when you're towards the end of the sequence. Yeah. Yes.
After we train this value function, how do we compute B from?
So the output of this value function is just the B. But note that there is no after we train the value function. It is being trained alongside the policy model. So initially, the value function might be pretty bad, and then it gets better and better as we see more samples from our policy model. Yeah. All right, let me check on. Okay, you have a question?
Yeah, so unlike the group method,
Yeah.
where we need to generate multiple models from X,
Yes.
this value function method, we only need to generate one partial response.
Correct. Yes. Yeah. So the group method is limited because it requires multiple rollout or multiple generations from the same prompt, which might not be the best use of your compute. You might want to diversify your prompts instead. So yeah. All right, so let me, oh, I already wrote a J here. Okay, so we also saw this in the last class where now I'm just going to write this expectation over all prompts from our data set as well as y's drawn from those prompts in response to these, y's drawn from our policy in response to these prompts. And again, we are trying to maximize the expected reward, but then this is the thing we talked about at the end of the last class is we also want to subtract this KL divergence term, which is larger if we're deviating too much from our SFT model. And again, we motivated this by kind of countering reward hacking and countering losing a lot of the desirable properties and like factual memorization task capabilities that are already present in our SFT model. So again, remember that this KL term here, the beta is a hyperparameter which you set yourself. This was just equal to the difference in the log probabilities. And note that this is actually the reverse KL divergence. So I wanted to talk a little bit more about that. Depending on if you compute the log of P SFT minus log of P theta or log P theta minus P SFT, you will get different behavior in the underlying model. So I wanted to just show a quick plot, and then we can come back to our discussion. Okay, so let me refresh this. So this figure shows both the forward KL divergence and the latter, where here our target distribution is this bimodal, the thing that you see with these blue lines here. So let's call that our reference distribution. So in our case, it's going to be the PSFT. So this is the thing that we don't want to deviate too much away from. And the red is what our model is doing, our P theta, our policy model. So the general idea is that if you're doing the forward KL divergence, which is the PSFT, log PSFT minus log P theta, you will get to this kind of mode covering behavior where the model is going to try and distribute its probability to cover both of these peaks. And here, the model that you're training is a little limited compared to the target distribution. So let's say it cannot exactly model both of these peaks. It's just using one Gaussian to do this. And so it can either pick one of these two modes or try and cover both of these modes. So the forward KL, this thing goes back to, you can see here that, well, at the beginning, it tried to distribute its mass kind of evenly across these two modes, whereas the reverse KL, I don't know what's actually happening to this animation. It will start covering just one of these modes. So the idea is that here we don't want our model to try and imitate all of the SFT model's behavior. That just might not be possible, but instead we would like the model to find a solution that maximizes the reward, but is also somewhat probable under our SFT model. I think I messed up these animations somehow, but yeah, that's the general intuition that we wanted to discuss. And so the reverse KL is used for that reason, but as I mentioned in the last class, there are many people who have tried both forward, reverse, different approximations, and have found very conflicting results. Actually, there was a new paper that came out last week that essentially said that both of them are not ideal, and here's a new thing that you should do to make this better. And some variants of GRPO that we're going to be talking about later, they simply just drop the KL penalty entirely and say, well, we don't actually need this empirically when we set up our data and training objective in a certain way. So lots of, I guess, conflicting results on the necessity of the KL penalty and how to implement it, but this is the most common one, also the one introduced in the OpenAI paper. Yeah.
On YouTube, there was a comment about that there was an error in streaming.
Oh, okay. Thank you for. Oh, the MacBook is not streaming properly. Is it working now? Oops. All right, I will assume that it's working and check back in a minute. Okay, so we've talked about the KL penalty, but unfortunately, we're not done yet with changing around our objective. Want to stabilize training with small updates during RL. And so, let's see. Oh, I probably just messed up the sharing of the blog. My bad. Okay, I will link the blog on the website after this so we can see what happens there. But I want to introduce this new concept called the policy ratio. And this is kind of a central part of PPO, which is the algorithm that was used in the initial RLHF paper. So I can just write that out here. PPO is proximal policy optimization. It was developed by John Schulman and people at OpenAI in like 2017, and it was developed for playing like Atari or some sort of video games, not for language models. Coincidentally, John Schulman now works at Thinking Machines, which produced the Tinker product that all of us are, well, some of us are trying to use now with varying success. Did you have a question? Yeah. So the question is, if we're fine-tuning, using our gradient update from reinforce, and we use a small learning rate, isn't our model just not going to deviate too much? That might be true, but with continued training, you will still start stepping, because you might have competing objectives where there are areas of the output space that yield a very high reward that you could get to with a very small learning rate just by taking steps over there. But those areas would never be produced by the SFT model, probably because they don't make sense. They might be ungrammatical or have all these other artifacts that your reward model is just not capable of scoring them properly. So the idea is that this explicit term here prevents the model from going into these degenerate areas of the output space that have artifacts that kind of the reward model is oblivious to, but the supervised fine-tuning model would never produce these. Yeah, so you can certainly do some number of steps without the KL term with a small learning rate, and maybe your model won't degrade or deviate too much, but that's kind of a crapshoot. It depends on your data as well. All right, so let's get back to this. So far we've been talking about the KL divergence term, which kind of penalizes the model from deviating too much from the SFT. But the policy ratio is intended to measure something different. So this is denoted by this rho, which sadly looks very similar to P, so hopefully these notes are legible. So it's computed at every token position of the response. So at position I, we will just compute the ratio of yi given all the tokens before I and x over, and now we're introducing a new thing, which is this p theta old. So this, remember that when we are updating our policy, every time we get a batch of prompts, we generate some rollouts y, some responses y for each of those prompts. We're doing that with a model that has not been updated on that current batch, right? So in general, when we are doing this RL training, for a given batch, we might do several different optimizer steps. And so as soon as we do a step, we're going to change the model's parameters so that they're no longer the same ones that initially generated those y's, right? And so one of the ideas behind this PPO algorithm is that we don't want our model to take steps that would make it very, very different from the previous policy model that initially generated those rollouts. And this essentially is all with the intuition of stabilizing training and not moving too far away from any given checkpoint of the model at any batch. So basically this theta old are the parameters of policy prior to update on the current batch. And so p theta is now any set of parameters that has undergone one or more updates on that batch. So here, this policy ratio, did not practice writing these rows, equals 1 prior for the first step on the batch, where theta equals theta old, and then it deviates on subsequent steps. Okay, so here, like for a given batch, I initially will set theta old equal to theta, and I'll just do a normal update using the gradient that we computed before. But every subsequent time I want to do an update over this batch, if I want to use the same rollouts, y, that came from that theta old model, I'm going to compute this ratio just to monitor how much I'm deviating from the model that generated those y's to begin with. And we will see how we can use this ratio in our update. Okay, so intuitively, this measures how much more or less likely is this token, say yi, under the new policy p theta versus the policy p theta old that generated it. And what we're going to do with this ratio is essentially use it to weight our advantage computation and control the magnitude of the update by clipping this ratio. So we're not going to allow this ratio to exceed a certain threshold. And if it does exceed that threshold, we're not going to apply any update to our model at all. So that's kind of where we're going, and that's the core idea of the PPO algorithm. So without this kind of computing the policy ratio and clipping it, people were starting to observe like very unstable training. RL itself is a very, very tricky and unstable algorithm. It depends on so many things, right? How good is your reward model? How good is your value function? All of these are extremely complicated tasks that those models are performing. And so while it might seem like, well, why do we have all of these safeguards in place? Why is it, what happens if we take these out? People have done like decades of research to come up with these kinds of ways to stabilize the training process. Yeah.
So how does this differ from like the KL penalty?
So remember, the KL penalty is strictly applied on the SFT model. Yeah. And also, as we'll see, the way that this is used is very different than the KL penalty. So it's used to control how much we increase or decrease the probability of a token at any given time step. So let's, yeah.
Also, is the theta old, like what part of which step is it from? Is it like from the step before the current one or from the beginning?
Yeah, it's from the beginning of that batch.
Okay.
So it's not from the very beginning of training. Otherwise, it would be set to the SFT model. Yeah. Okay. So the idea is we can weight our advantage. Remember, the advantage is the reward minus the baseline by this policy ratio and control the update, our gradient update, by clipping it. And so we'll now kind of define what we mean by weighting and clipping in the context of our advantage. So first, let's say that we have this, just for simplifying our notation, I'm going to roll that KL penalty into our advantage equation. So if we have, so we'll call this A KL, which equals our normal advantage, the reward minus the baseline, and we'll subtract this KL penalty. So I don't want to write this out over and over again. So then we have our J theta equals, and here it's important now that we're dealing with these token level policy ratios to kind of rewrite this whole J in terms of token level rather than sequence level. So all of these are sequences. But we know that a sequence is just, we can sum up the contributions of the KL term at every token. And we know our log probability also becomes the sum of the log probabilities at each individual token. So we can write this J as the, when we're writing the expected reward. Here, we'll just sum over the token positions, and this is where we introduce our policy ratio and our clipping. So this is the term in PPO, where we're going to take the minimum of the policy ratio I times our advantage at any given position I. And we're going to compare this to this clipped term. Sorry, this is getting complicated. There's no way to avoid this. Where we have the we're going to clip our policy ratio to be between this 1 minus epsilon and 1 plus epsilon range, where epsilon here is a hyperparameter. It's generally set to something like 0.1 or 0.2, meaning that if our policy ratio falls outside of, let's say, 0.9 to 1.1, we are going to clip it to be either the bottom or top end of that range. So we're not going to allow this policy ratio to expand outside of that. And we're going to then weight our advantage with this clipped policy ratio and complete our minimum here. So this looks complicated, but if we break it down, we can start to see what this is actually doing in terms of the updates to our model on particular tokens. So maybe we can start with some intuitive explanation of this and then get into a concrete example so that it becomes more clear. The general idea is that if the advantage of a token at some position I is greater than 0, that means we like this token, right? It is part of a high reward response, and it's not deviating too much from the SFT model. And so overall, if this quantity is high at a particular position, we like this token and want to increase its probability. However, the max increase is going to be proportional to this 1 plus epsilon times the advantage. So we are not going to let the update get out of control. At most, we might make this token like 1.1 times more likely to occur in this context than before. If we didn't have this kind of clipping, then we might allow, like, if our advantage said that this token is should be, 10 times more likely than the previous policy that generated this token, we can easily get into areas of the output space that result in like poor quality completions that have high reward overall. And similarly, if this quantity is less than 0, we don't like the token. It was part of a low reward response, like a worse than usual response. So we want to decrease its probability, and here it's going to be capped by, 1 minus epsilon times this. So the key thing to note is that when clipping is applied, no gradient will flow through the clipped term. And so the idea is that if the model, if your advantage is really high and the policy ratio after you do an update is also really high, you don't want to increase the probability of that token any further because it's already very likely. And so maybe you don't want to do an update and update other things that are less likely than your prior policy. So let's actually just look at an example that will hopefully make this more clear. So let's say that I set this epsilon to 0.2. So our clipping is between 0.8 and 1.2. So we're going to clip our policy ratio to fall between this range whenever it exceeds it. All right, so let's take a look at some cases where the advantage at a particular token is positive, meaning this is a good token that we want to increase the probability of. So here we can look at two cases. One where the policy ratio is outside of the clipping range, right? So if we compute the weighted advantage, the policy ratio weighted advantage, the unclipped term looks like 2 times 1.3, which is 2.6. Whereas the clipped term is going to first clip the policy ratio to 1.2 and then do this multiplication. So it's 2.4. And we see that in our equation up here, we are taking the minimum of the unclipped and clipped term. And so in this case, we are going to take the clipped term, because it's the minimum, and no gradient will flow through this so it's already more likely than our threshold would restrict it to be. It's already more likely than it was under the old policy. So basically this is saying we are already good on this token. We don't need to increase its probability even more because other updates that we've done till this point have already increased its probability enough. Yes? So in this case, yeah, because the policy ratio fell outside, it was higher than our maximum. But as we'll see, if we have a case where it's negative, right, the policy ratio is less than 1, which then we will clip it to the bottom end. Okay, so this is saying that, we know this is a good token, but its probability has already been increased over our threshold, so we don't want to do anything else to this token. Now, if we have the same case, except we have a lower policy ratio, now it indicates that this token is not as not likely as in the first case compared to the old policy. So the unclipped value here is 2.2, and the clipped value is still 2.4. And so here we're going to choose the minimum, which is the unclipped value, and the gradient will flow through here. Meaning this token is currently so it still can be increased to increase its likelihood over the old policy. We still have some room to go before we hit our threshold. So let us do a normal update to this token. So let me just, complete this, increase the probability of this token at position I. So we could do the same thing for the negative advantage cases. So these are cases where we want to decrease the probability of this token because it was associated with a worse than usual sample. So here, let's say this policy ratio is 0.6, right, which is already lower than our threshold. So here we have an unclipped value of minus 0.2 and a clipped value of minus 0.6. Now we already know that this thing is outside of our threshold, and we're choosing the minimum here, so no gradient flows because we've chosen the clipped value. This means that this token is already, its likelihood has gone down enough. We don't need to further update it. And just to complete the picture, if our policy ratio falls within the threshold, so let's say 0.9, then our unclipped thing will be minus 1.8, and the clipped will be minus 1.6, and we will choose the unclipped normal gradient, and this will lower the probability of the token because we didn't like it. It was bad. It had a negative advantage. All right, so before I conclude this part, I will just plot out all of the different cases that could happen given the sign of the advantage, is it positive or negative, and also whether or not the policy ratio falls within this the clipping region. Okay, so here let me just plot our advantage. And so I'm also going to draw the thresholds here for our policy ratio. So say we have this, and let me just write this a little cleaner. So the J will be on the y-axis, and our policy ratio so this is 1 minus e, 1 plus e. We'll center this at 1, and the x-axis here is our policy ratio. And so there's two cases that we want to plot. One is the advantage at a particular token is above 0, right? And so basically we want this thing to make no updates once we've exceeded the 1 plus epsilon policy ratio. So the advantage will start at 0 and gradually expand until we hit the end of this what's called a trust region in the literature. So this part you can refer to as the trust region. And then after that, once it exceeds this quantity, we're going to do no more updates. So that is represented by this flat line. The advantage has been clipped. So on the other hand, when we have a negative advantage, now we want to stop making updates once the policy ratio has decreased past the lower end of our threshold. So here, let's draw this like this, and then as we hit this, we will continue to decline this way. So just to be clear, why are we continuing to decline over here in this part of the plot? Any ideas? Why do we want to continue to update our model to lower the probability of this token if our policy ratio is greater than 1 plus epsilon?
It was so bad that we wanted to be like have no probability.
Well, it's not, so the advantage is already less than 0 for all of these red, anything on the red line. So we know the token was bad. The thing is that if our policy ratio is above 1 plus epsilon, that means that the token is now way more likely to be produced by our current policy than the old one. So our current policy is actually doing the worst possible thing, and we need to make an update to decrease that probability. So that's the reason. It's the same with things over here, right? Here, the new policy is assigning lower probability to this high advantage token than the old policy, so we need to keep improving it. Okay, so I guess I will stop here. Very poor time management. I did not get to the actual thing that I wanted to talk about, but actually that's not super fair. So the GRPO algorithm that we'll talk about now next time is essentially a variant of this PPO algorithm with all the clipping and the KL term and stuff. We're just going to simplify the reward and the baseline, the value function. So for the next couple minutes, I can take any questions about this. Yes?
So I have two questions. Here in the new J function that we created for per token,
Yeah.
n would be the number of tokens that we have.
Yes, sorry, that's a good point. So here, n is the number of tokens, so the length of the sample y. And note that this is not a new objective, it's just a rewritten version of the same objective that we have.
And the policy ratio, so we're dividing the new model over the previous model for the same response, but how are we sure that the new model is going to generate that same response, the yi?
So that's, the question is, how are we sure that the model is going to generate that same response? We don't need to be sure of that because we already know the yi that was sampled from we have the y, right? It was sampled from the old policy. In order to compute the probability of this y under a new model, you simply have to just pass it in as input to that model, right? And with masking, you can predict the probabilities at every time step. So yeah, it's actually easy to compute because you don't need to do step-by-step generation. Yeah. Other questions? Let me check on YouTube. iPad part is okay. The issue was when you switched the blog. All right. Great. So next time then we will get a little bit outside of the weeds and talk about how we can apply this algorithm to simple verifiable tasks, which will allow us to get rid of the reward model completely. So for example, in a math problem, if I ask you what is 8 plus 8, I don't need a 8 billion parameter reward model. to tell me if the answer is correct or not, right? So we will look at all of this stuff that we talked about with the policy ratios, KL divergence, advantage, and so on, but then start simplifying it to work with reasoning, which is a new concept that we will discuss next week. So yeah, and also you will have a homework going out sometime next week that has you use GRPO to train a very tiny language model on one of these like easy to verify tasks. So still working on that, but it should be fun. So keep